I was totally like just so excited that nobody's gonna be missing my fourth period, and I forgot. Okay. So anyway, the sun gives us the every wavelength known to man, which means that it has a full continuous spectrum, no gaps in the rainbow here. And that's important because different life needs different wavelengths of energy that they can consume or use. So chloroplasts use like blue light and red light more so. Phytoplankton might use something else. Butterflies see in UV, so they have to kind of be able to use that. That actually has nothing to do with light. That has to do with energy. Sorry, I'm sticking with visible light here. So anyway, we have to have that from the sun. But elements are going to give off different emission spectra, also called bright line emission spectra. Okay, so that just identifies the element if you know exactly which bands relate to whom. So you're going to see hydrogens today. Hydrogens is the simplest because it is the simplest element, meaning that the electron transitions, each line represents electron transitions. It just means that hydrogen has fewer possibilities for electron transitions. Because how many electrons does it have? One. It's got one electron. So hydrogen having one electron means it can move up from n equals 1, which is energy level 1, up to n equals 2 and back down, or up to energy level 3 and back down, energy level 4 and back down. So it can move a couple of different energy levels. And I know you're saying, well, hydrogen doesn't even have any energy level 3, 4, and 5, and so forth. It doesn't, but they're always accessible, meaning that they don't have to portray them at all times, but they can always jump energy levels that are kind of imaginarily there until you have an electron in there. So when I say here, electrons moving from one energy level to another, the color is going to be coming back at us. How do we know which color? We have to know the energy related. And then we can go back and backtrack to frequency, and then backtrack to wavelength. So that's the only way you're going to know the colors, if you know the wavelength that's given off. Or yeah, the wavelength. And you'll notice that I have a picture on the next slide. There are very, very set specific energies that can occur, or energy transitions that can occur. And that's because the energy transitions are quantized, meaning that they have a specific amount of energy. Quantized means specific amount of energy. Sometimes I think we talk in like olden times, quantized, I don't know. So this means that energy level 1 has a set distance from energy level 2, which has a set distance from energy level 3, and so forth. That's what I mean, quantized, specific amount of energy. So on your equation you wrote yesterday, using Planck's constant, this was energy change of a photon. That is what we are calculating. This is regarding one of your questions on your homework. Some people ask me this, and I'll go over it later. The energy that we're talking about that's related to this frequency and this Planck's constant, that is called energy of a photon. One photon, meaning that if you wanted to find something per mole of photons, what relates from one photon to a mole of photons? What conversion? Avogadro's number, 6.022 times 10 to the 23rd photons per mole of photons. So that's good to know for one of your questions. Anyway, we can obviously implement wavelength into that as needed. Spectroscopes work like this. They use a diffraction grating. This is a glass prism. As this is the hydrogen spectra, this is the hydrogen gas. As it goes through a small slit, which is a spectroscope, and it goes through the diffraction grating in the spectroscope, it relays and separates the wavelengths of light into their different quantities, and marks it on there's a detection grating that's going to show up. And that's what we see. We can see hydrogen has 4 spectral lines, very simple, 4 only. And we're going to see how these transitions occur in the lab.
Can you scroll back up?
Yeah. Here?
Yeah.
Okay. So that's like the background on how spectroscopy works. And then we're going to do calculations with the Rydberg equation. I always say Rydberg, but it's Rydberg. Like I always said, nursed. Nerds. Don't read.
These chemists aren't well in the grades. You're good.
Okay. So just like we were I'm going to show you the Bohr model first. Bohr model, set path. As you transition from a far distance out, as you transition from a far distance out and then drop back to ground state, this is excited state, and this is ground state, there's going to be a large amount of energy transition loss, and that's going to correlate to a higher energy wavelength, like violet light versus red light. So that's how we kind of just talked about this. The transitions are going to be based on the transitions are going to create a specific amount of energy, That's proportional to the distance that the drop was. Higher drop, higher energy. Higher energy, what wavelength? Smaller or larger? Smaller wavelength, right. So I'm not staying here forever. I'll come back here if you need. I just kind of talk about that a lot. But this is a really good one of oxygen. A lot more electrons, obviously. Neon's a lot more electrons to work with. This is the new stuff from AP Chem on this bottom part of the slide. You can see that I have energy levels denoted here again. Energy level 1 through 7 right here. Energy level 1 to 2 we talked about yesterday was a huge gap, and so forth. It kind of crunches as it goes up. There are different series of wavelengths that are put off that fall in different categories. Light, IR, X-ray, UV, they fall in the categories because the more energy that's dropped, or sorry, the higher the transition relates to more energy, which relates to different parts of the EMS, right? And people have put names to these. They are called, so I'm going to show you down here first. Dropping from wherever you are to energy level 1 is called the Lyman series. So dropping to energy level 1 from wherever you are, and I'll show you in the images here in a second. It's called the Lyman series. I just remember Lyman low. This is me over here making up some crazy stuff to help you memorize these series. That gives off IR energy, infrared. I'll show you the pictures in a second. Actually, I'll show you the picture now. So here's Lyman. Wherever, and this is a better image, I think, even though it's really fuzzy. Wherever they are dropping from, and they're dropping to the lowest amount of energy, the ground state of n equals 1, that's called the Lyman series. So anytime they drop to 1, that's the Lyman series. Anytime they drop to the second energy level and don't go all the way back down to ground to the first energy level, they stop at second, that's the Balmer series. And anytime you drop from wherever you are to the third energy level is the Paschen series. So the way that I remember this, and you can see on this one as to what it's labeled, because the UV is the, oh, hold on, I wrote IR. UV, because I was thinking it was the highest energy. Lyman is UV energy. I knew Balmer was bi, because I always remember we're binocular vision, as you can see with that. Bi is, Balmer is visible, and then Paschen is IR. Sorry, I just added these just a second ago. This is, what did I just say, UV, and this is IR. Because this is the longest energy drop all the way down to n equals 1, so that's correlating with the most energy. Most energy would be the UV side of the visible spectrum. Balmer, so here's how I remember this. Balmer is dropping to the second, that's bi, Balmer bi, 2 is bi. And then that's our binocular vision. You can see that, it's visible light. That's my cheesy way of remembering that one. So binocular vision. And then Paschen, remember organic prop? That was our 3 carbons. I just said I had to figure out something, so N is equal to 3 is propanol or prop in organic nomenclature, so Paschen was the third one. And that's just the shortest drop of energy, so it's the less energetic side of things, which is going to be the IR spectrum, or IR EMS. Okay, here's the formula part of this. So we actually want to quantize, we want to calculate, get a quantitative number that correlates with the energy, and that's called the Rydberg, I always spell it wrong, formula. And I'm going to show you this one and then a variation of this where that relates to 2 different ends. So this is the mathematical equation used to predict the wavelength, because as we already know, you can relate any of these things. You can relate energy to wavelength and back and forth. So if we can figure out the energy transition, we can figure out the wavelength and figure out what wavelength of light that correlates to. So this is mainly concerning hydrogen. We're going to only work with hydrogen because this is kind of related back to the Bohr model as well. And here, and I have this down here and down low in just a second, but whenever you see this equation, the Z number, don't forget, represents the number of protons. In hydrogen, what is always the Z number? Say again? 1. So this Z is always 1, which makes math easy, right? 1 squared is 1. And then in the Rydberg equation, the N down here is called the period number. That's what the quantum mechanical model, when you guys were reading in your pages 1 through 16, the N number is the period number or the energy level. It's truly the energy level, but energy level. but it's also related to the period number, as you see in when you do electron configurations. Usually the energy level and the period number are one and the same. The RH value, that's this constant right here, I don't know if you can see this, is 2.187 times 10 to the negative 18th power. And that is a constant that will be given to you on your AP exam. It's not a constant to memorize. And it's negative. And then I note over here as to why it's negative. A negative is helping to show that it helps with understanding why the energy levels have different amounts of energy. The ones that are closest to the nucleus, so this is the nucleus here, and you're talking about an electron right here, it just so happens to be the same size as my nucleus in this picture. This negative value means that the energy, or the energy of that electron is less energetic. So the negative value, don't be too concerned about that, but it means that the electron is really close to the nucleus. And when we talk about the transition, I think it'll make more sense versus just the plain old energy level. Because this equation as is, this energy is the energy of a specific energy level, or the electron at the energy level. It's not talking about a change in energy, y'all. This is just very specific to the energy level energy. But we are always more concerned about the transition, about the change in energy. So here's the adapted version. Can I go down? Okay. The adapted version is, so this is what we just wrote down. I modified this from our previous version because you can see that I said the RH is that, so I plugged it in, and then that Z number squared is always 1, so I just ignored it pretty much, and I put it over N squared. So I like this one because it's a bit more simplified of what we just wrote, and that's the energy level, or that's the energy of the energy level. And then if an electron is moving, then you're going to have a change in energy from two different energy levels. So you always do final minus initial like you do with temperature, so energy final minus energy initial. But this is a lot to write out, RH, and then 1 over the energy level final minus RH value, negative RH value of 1 over the final. So when you, combine like terms or move your constant out, it actually ends up, that looks like a really huge equation, but it's not. It's actually just this. RH value times 1 over N squared final minus 1 over N squared initial. Because this negative in the front offsets the negative of the negative value RH. So I'm going to explain the negatives in just a second. It's at the very bottom. And this is going to be the energy that's given off by the electron that is falling. And as the electron that's falling releases that energy, if we can see it, then we call that a photon. Because it's a packet of energy that's related to the wavelength of a specific amount of light. So that's called energy of photon yet again. And then energy of photon can be related back to wavelength via de Broglie's equation, or the combination of all the speed of light formula and the E is equal to Planck's energy relation. So you can relate everything back together. So anyway, just making sure, if you have a change in energy that's negative, that means it's falling. That means the energy transition was releasing that energy. And if you have a positive value of energy, that means it didn't release the energy. That means it did what? Right, absorbed it. It just jumped up to an upper energy level. So the way that you're going to end up with a negative value is if your final is lower or higher than your initial. If you're releasing or emitting energy, the electron is falling, right? Back down to ground state. So it means the final is a lower energy level than the initial, and then vice versa for the other. Okay, so let's do a problem. Calculate the change in energy of an electron that moves from n equals 5 to n equals 1. Energy change is equal to what? What's your formula you just wrote down? Hold on. I'm just going to put RH if that's okay. I'm going to write it in two ways. RH 1 over n final squared minus RH of 1 over n initial squared. But then what do you do with the RHs? Right, you pull them out to the front, right? So change in energy is equal to RH 1 over n final squared minus 1 over n initial squared. And then the n, RH is 2 point, what was it, 178. I actually don't show any, I show my setup, I have no math here. 178 times 10 to the negative 18. And then 1 over n final would be 5 squared minus 1 over n initial, which would be 1 squared. So then when you calculate backwards, I'm sorry, yeah. I don't show this up here. 1 squared and 5 squared. And then that's going to give you a negative, this is a joule unit, by the way. I didn't show that in the previous slide, I don't think. That's going to give you a negative, RH value is negative. Negative 2.09 times 10 to the negative 18 joules. So what is the negative actually indicating to you there? Right, and you knew it was going to be emitting energy because what's happening to the electron? It's falling, right? It's falling from 5 to 1. Yeah.
Why is there a negative RH value?
Because the RH value is a negative value. Sorry. This value is a negative value. This, I think, this is 1 and minus a, huh?
I'm looking at it.
Okay, I can't see you. Okay, so anyway, I sometimes will have to double check myself with the negatives, but I know I'm always right when I have a dropping energy level and it's releasing and I have a negative joules. You always will have that correlation. That will always be true. So yeah, there again, energy is lost. And sorry, this is important because the energy, relating back to the third law of thermodynamics, energy lost to the universe means that whatever you have left is more stable. That's the only reason that we want to make sure that our energy relation is right, because that's following the third law of thermodynamics. So knowing this energy, that is the energy lost, but the actual energy lost is the absolute value of that, right? It's 2.09 times 10 to the negative 18 joules. That can be used to find the wavelength. What wavelength, or how would you get the wavelength from the energy? Tell me how you would set up. Loud and proud, people. Equals HV. Okay, is there C over C? How about you? Can you rearrange to wavelength is equal to HC over E? Oh, there we go. E. There you go. Trying to make my line and my E the same. So rearrange because you want to find wavelength. You're looking for wavelength. So then you would plug in 6.626 times 10 to the negative 34th joule seconds times 3.00 times 10 to the 8th meters per second over energy, 2.09. And so we're taking the absolute value of the energy because you can't have a negative wavelength, right? There's no such thing as negative length. So that's why I said just remember that the negatives is there to tell you how energy is released or absorbed, not truly if that's a negative energy. Okay, so then the joules cancel out, the seconds cancel out, leave you meters. Yay, meters are 9.507 times 10 to the negative 8th meters. And then you could figure out that this is, you could look on the electromagnetic spectrum to see what type of wave that would be. Okay, let's do our lab. Because then after that, I'm going to go over quantum. Quantum will be, I think, quick and painless. I think. All right, so the lab is in your packet. I'll proceed to set up, and this will be your lab. Come back here when you're ready. So these labs are very, like a paper review lab. They don't take one home. They're more maximum. Yeah, you can. I don't care if you want the doubles or Hydrogen, spectrum. Okay. So the very first thing it says to do in the lab is what? I don't know. Hydrogen spectrum. So point the spectroscope outside the classroom. That means go look at the sun and come back.
Look at this.
Now? Alright. Oh, look at that. Do you guys know how to use these? I'm sorry. Okay. The Carolina must be, listen, Carolina must be pointed up. Your job is to point whatever you want to see that has to go in that slit. The slit bounces out in here and you look through and you'll see that on the left-hand side, you'll see a rainbow. You'll see numbers right below the rainbow. You see numbers right below the rainbow. Alright. That's going to point you to the pot of gold underneath. This one is the one that's, this is the top three. Okay. So if you want, go look at the sun, come back and I'll show you hydrogen. Somebody hold the door. Yeah, she gave him out during class.
Oh, okay. Did she? I wasn't there. I was in the
Yeah, I know.
It's just like
Is it red?
I'll help you.
I had 3 students last year. You can do that with
do you know Justice Tucker?
I don't know who that is, but
He's really bad. I'm not that bad.
I went to school with a named Justin Simon, so she said that way.
Did you really?
Bye. Okay, so you saw full continuous spectrum. Okay.
I didn't know it was going to work, so I was waiting for the line, but I was like, I can't find it. I was like, it's supposed to go that way.
I'm going to answer these lights for me. Jesus light and everything.
Oh, that's one of the
Jesus.
It's something like 5 years.
I started talking to that all the time. Alright, come to the light, people. Okay, so I'm trying to cut out a couple of the calculation part of this because I think we've seen a couple times you got this. But the first question that said, go see the continuous light spectrum, and it says write down the wavelength. People are not write down wavelengths. Every wavelength is man with you forever. Okay, so do not, number 1, it was just go outside. Number 2, you have to look at the hydrogen light and you have to write down the wavelength, you have to write down the number in the spectroscope that correlates to the line you see. And then question 1, it tells you what the line in the spectroscope means. The line in the spectroscope is the unit place. But we need the unit. The line in the spectroscope is worth 1,000 angstroms. Angstroms is the unit of what measures the light. So that's what's in your lab. So I need you guys to kind of take turns seeing this. I'm going to turn this on. You have to really align it. So you're going to do some cheerleader squats, and you down here, and really align that slit in your spectroscope with this, okay? So you need to write down some stuff. So I'm going to say go to the front where the light is and write down stuff. Because if light is big, it's really hard to see. So take turns, get up. You get up, come in. Pull us first, don't get any time. Get over here. And you're going to have to write down, shout out, and write down further. Shout out. I don't know. I just meant like. Whoa.
Someone just screamed up real loud.
I can see the color.
Okay, we have 5 points. Let's see the 5.0. Yeah, I was gonna say 5.0. Okay, 5.0, right then. Okay, so the red is at 5.0. Where's the blue?
I mean, I have blue and violet.
Okay, give me one. Okay, come on.
Oh, there we go.
Okay, the red is 5.0. Okay, keep going. So what's lower than that? Give me the blue. The red, okay, so the red might be below 5. The red might be like 4.9. Okay, continue with blue. I have to turn this off and say red is 4.9 or 5.9. Teal. Teal is where? Yeah, at 5? I thought it was 5. Oh, sorry. The red's gonna be on the 7 side, right? Yeah. I'm sorry. Red is at 7.
Oh, I see it now. And then the violet side will be 4.4.
So where is mine? So we decide. 5
Teal.
5.0 is teal. Okay.
Okay,
I'll be the last one.
it's right between the 6.5 mark and the 7.
So red is 6.8. So yeah. So red is 6.8. Violet at 4.7. Violet at 4.7. And 4.4.
Now I see
And
it.
4.4. Okay. And then violet. Alright.
Oh, yeah, I see that. 4.5. No, I need to see it perfectly now.
I just feel
More than
violet.
half a violet. Yeah. 5 is teal. How come I think like right here?
No, the lemon is. I don't know.
I am.
Sarah.
I raised that in the
You said what numbers did you? 5.0 is teal.
I got like 4.4.
4.5. And there's also a 4.3-ish at purple. And then 6.8 is red. Yeah, I think we got one. Good. Yeah. The thing is real hot. Right here. Now, go write the numbers on the board that we just talked about, and somebody, you guys can start doing the rest of the I think that's only dad. Yeah. I'm going to write numbers down. Sarah, I'll have this number.
Am I still videoing?
I'm gonna laugh.
Wait, it's what?